One, I'm Surathep Kyohom from Chulalongkorn University. Today, I'm your host, and again, this is our webinar series. And today, it's our pleasure to have Professor Wei-Ren Liu with us to give a talk on a very important topic of related to lithium-ion battery. So, Professor Wei-Ren Liu is a professor at Yuan Christian University, where he is currently leading a research group on energy materials laboratory. He received his doctoral degree from the National Taiwan University in 2006. He worked as a researcher at the Industry Technology Research Institute from 2006 to wow 2011. His main research interests include lithium-ion batteries, sodium-ion batteries, solid-state batteries, and graphene-based material, as well as luminescence material and perovskite quantum dot. So I think now it is time for the talk. So Professor Liu, can you come on the stage and take a control?
Professor, I think Professor is offline, appear to be offline.
Oh,
Could you please
so
let
sorry,
him know to come back again?
sorry, sorry everyone. So just we have technical issues. Just one moment. Yeah, I will try to invite him back. Please wait. I'm contacting the Professor Liu. Just one moment.
Sorry for the
Welcome back.
disconnect.
Welcome back,
Okay,
Professor. Okay, now
okay,
you take the control, please.
okay. So can you see a screen?
Yes, colorful.
Okay. Okay, so first of all, I would like to thank Professor Sora Tap invitation. So today I would like to talk about our recent work about the surface modification strategy to enhance the battery performance on lithium battery. I'm Wei-Ren Liu from Chung Christian University in Taiwan. So in this talk, I will divide it two parts. The first, after introduction, I will introduce two different examples. The first one, we use the plasma modification on soft carbon anode for the lithium battery. And the third part, I also try to transfer from anode to cathode. We also use another approaches to modify the NCN A11 cathode for the battery application. And finally, I will give a conclusion. So as we know, there are many advantages, including small size, light, high safety, and longer operation lifetime, and high stability. So the lithium battery have been widely used in our daily life. So here is the working principle of lithium battery, including the cathode and the anode. So it's very important to enhance or improve the the property of cathode and the anode to get a much higher energy density. So during the charge, the lithium will diffusion into the anode to storage the energy. And for the discharge, the lithium will go back to the cathode. So it's very important for the interface to for the surface modification. It could be not only enhance the reversible capacity, but also could enhance the safety issue. So first of all, we can to talk about the anode. So the anode for the lithium battery, including the intercalation anode, alloy anode, and the conversion anode. For the intercalation, such as the graphite, it's a very good cycle life and low cost. However, the capacity is not so high and the low energy density. So for the alloy, such as the silicon and the tin, they has a very high specific capacity, high energy density, and good safety. However, uh, for the alloy, it is a very large irreversible capacity loss at the first cycle, and also dramatically modern expansion could reduce, enhance the poor cycle stability. For the conversion anode, uh, like the metal oxide, it has a high capacity and low aberration potential, but the cycle life is not so good. So in this study, so the key issue for the lithium battery in anode, including two parts. The first one, because commercial carbon electrode is hydrophobic, so it's very poor for electrolyte weighting. And also for the graphite layer structure, is not good for the lithium diffusion, so it will give a very poor rate capability. So our innovation will be three part. The first one, we use the soft carbon to replace the graphite because the soft carbon has an amorphous structure, so it's good for the lithium diffusion, and it will get a very good kinetics. Also, we use the atmosphere plasma assistant nitrogen doping process to not only to create some oxygen functional group on the surface to become the surface from the hydrophobic to hydrophilic. Also, the nitrogen doping process can enhance the electronic conductivity of the soft carbon. So we try to take a look at the literature review of the plasma technology on lithium battery. As you can see here, including the lithium titanium oxide anode, nanosilicon, and nitrogen dope graphene oxide MOS2 composite anode, and also NCN cathode. They all use the plasma technology to make a surface modification and enhance the cycle life and the capacity. Also, recently for the lithium metal anode, this report, they try to use the nitrogen plasma to make a lithium nitride coating on the surface of the lithium metal to inhibit the lithium dendrite. So as you can see, by using the nitrogen plasma surface coating, the flower-shaped lithium nitride could be very beautiful coating on the surface of the lithium. Also, the modulus is as high as the 50 gigapart. For the lithium stripping and planting after the lithium nitride coating, the cycle life could be extended to the 30,000 minutes. Also, another paper that tried to use the plasma treatment on the separator. So as you can see, without a plasma surface treatment, the surface is hydrophobic. But after the plasma treatment, the surface become hydrophilic. So it's good for the liquid electrolyte waiting on the surface. So it will be good for the lithium diffusion during the charge and discharge process. So why we would like to use the plasma? So the plasma in nature, including the sun, stars, and the lightness. So in order to create the artificial plasma, we can use the gas discharge. So just use the chamber, and we just give a gas discharge with different gas in the chamber. We can to create the artificial plasma to make a surface modification of the cathode or anode or separator. So the first example I would like to show is here we use the soft carbon. So we use a recipe here to make a coating of the soft carbon on the copper foil. After drying and press, and we can obtain the soft carbon electrode. So here we use the atmosphere argon plasma to make a surface modification. So we try to use, here is the condition. So we try to use 3 different kinds. For 0 means the pristine, the soft carbon electrode. And we try 20 times, 40 times, and 60 times to make a surface treatment. So it's a tornado type the plasma jet on the surface. So hopefully we can to make because it is a atmosphere the plasma treatment. So there are some nitrogen, oxygen, and the moisture in atmosphere. So hopefully we can make a nitrogen doping inside and the functional group outside to make a hydrophilic surface and the nitrogen doping inside the carbon materials. So here we use the SRD pattern to see the soft carbon electrode before and after different plasma treatment. So here is the soft carbon, is about 26, is an amorphous structure. So here its 3 peak is about the copper foil. So as you can see, with different plasma treatment kinds, the structure is very similar. It means that the plasma is only on the surface, it will not to attack the structure. It will not destroy the structure. We also use the Raman spectrum to see the soft carbon electrode before nitrogen, before plasma treatment, and after different times the plasma treatment. So as you can see here is a D band and G band. For the DG ratio, we can identify the defect in the carbon. So you can see before the pristine soft carbon, the DG ratio is about 0.78. After the 20 times, it will increase to 0.9. 14 times increase to the 1.03, and the 16 times is very similar, 1.01. So it means that after the argon plasma treatment on the surface, the defect will increase. So the increased defect maybe is benefit, so the lithium storage at the capacity increase. So we also use the SEM to see the surface morphology before and after the plasma treatment. So you can see here for the pristine, the particle size of the soft carbon is about 10 micrometer. So after the 20 times, 40 times, and 60 times, the surface morphology is very similar. So it's a little difficult for the SEM to see the change on the surface. However, we can see the water content angle. So you can see after the soft carbon 14 times the plasma treatment, the content angle reduced a lot. For the pristine soft carbon is a very high content angle. So, and we can see by using the plasma surface modification, so it's from the hydrophobic to the hydrophilic, and it can extend it to 2 weeks and can maintain about the 60-degree content angle. So it's good for the liquid electrolyte weighting in the carbon electrode. We also use the SPS to see the nitrogen and the oxygen bonding information before and after the plasma treatment. So first of all, we can see for the oxygen functional group, for pristine, the oxygen is 1.91. But after 20 times plasma treatment, increased to 11, 13, and 21. So obviously, by using the argon plasma treatment, so the surface functional group increased a lot. So that's the reason why the content angle dramatically decreased because of the functional group. And also, we noticed that the nitrogen also increased. So you can see for the pristine, there's almost no obvious the nitrogen signal on the surface. However, after the 14 times argon plasma treatment, so you can see the graphitic nitrogen, periodic nitrogen, and the pedidic nitrogen appear in the structure. So from this SPS spectrum, we can to identify we successfully to make a nitrogen doping in the soft carbon structure. So as we know, the nitrogen doped carbon could be enhance the electrochemical performance for the lithium battery. So we use the silicon voltammogram to see the first 3 cycle pristine soft carbon and 20, 40, and 16 times. So you can see with increasing the plasma treatment times for 40 times, you can see the current density increase a lot. It means that by after the plasma treatment could be facilitate the kinetics during lithium intercalation and extraction. But if we use more than 16 times, maybe it's too longer and the surface will be damaged. So the current density reduced a lot compared to the 40. So we also assemble the coin cell to see the rate capability and the cycle life at a different condition. So you can see here for the pristine soft carbon, the rate capability is not so good, but after the best condition 14 times, you can see even at the 10C rate, the capacity is as high as the 100 milliamp hour per gram. Also, the cycle life increased a lot after the plasma treatment. So here just show that by using the plasma treatment for 14 times, it will give a very good rate capability and very good capacity retention. So after 100 cycle, the capacity retention is as high as the 95.12%. We also to see the charge discharge curve at the first 3 cycles. So you can see pristine soft carbon, the first charge 276, and the first discharge 244. The Coulombic efficiency is 18.5. But for the 14 times the plasma treatment, it could be enhanced to the 293, and also the discharge capacity could increase to the 259, and also slightly increase the Coulombic efficiency to 88.63. Here shows the charge discharge curve at the different current density. From here, we also can see that the SC 14 times the plasma treatment have a very good rally capability. We also use the EIS to see these 4 samples at after the 2.5 cycles, and to see the impedance evolution before and after the plasma treatment. So here we use the equivalent circuit to fitting and to identify the impedance from the RSEI and the impedance from the charge transfer resistance. So you can see here, for the pristine, it's a very large impedance here, including the high SEI impedance and the high charge transfer resistance. But after the 14 times the plasma treatment, not only the SEI formation, the impedance reduced 1/2. Also, the charge transfer resistance reduced from 15 ohm to 30 ohm. So it means that the nitrogen doping into the carbon materials could be increase the electronic conductivity and also reduce the charge transfer resistance. We also use the ball plot to make a slope. We can to calculate the diffusion coefficient. So you can see before the plasma treatment, the diffusion coefficient is 10 times 14. But after the 14 times the plasma treatment, the diffusion coefficient could be enhanced 10 times. So by using the plasma treatment could be dramatically enhance the kinetics of the lithium diffusion. So here is the enhanced mechanism. So we use the atmosphere argon plasma surface treatment. So first of all, we make a soft carbon coating on the surface of the copper foil. So after different kinds of the plasma treatment, we can to make a nitrogen doping inside and the functional group outside. So after the argon plasma treatment, so it will be much easy for liquid electrolyte waiting in the carbon electrode, and could be enhance the kinetics of the lithium ion battery. So here, this video just show that we use the left hand side, we use the argon plasma treatment, and the right hand side is a pristine, the soft carbon. So you can see we just put the liquid on the surface. So it's hydrophobic, and the left hand side is the hydrophilic. So it's a very powerful technology to make a surface modification to make the electrode from hydrophobic to hydrophilic. In the future, we can use like this. If the scale up is possible in the future to continue to make a surface treatment by using this prototype the equivalent. Okay, So this plasma actually modify and the nitrogen dope the soft carbon just published in Electrochemical Acta 2022, and also we have a patent. And the second part I would like to share is to use the plasma assisted the titanium nitride coating on the NCN811 cathode for the lithium battery to improve the safe performance. So for cathode, is in the beginning, the Sony they announced the lithium cobalt oxide as a cathode. The lithium cobalt oxide is a layer structure and it's a very high working voltage and longer cycle life. However, because the cobalt is very expensive, so and the capacity is only one half the theoretical capacity, because the lithium cobalt oxide, if the lithium extraction one half, and the structure will collapse. And the second one is lithium phosphate. So it's a very cheap and very safe cathode. However, it's poor conductivity and low energy density. So right now, they try to use the NCN, try to increase the nickel content to obtain the high energy density and to reduce the cobalt to get a low cost. However, for the NCN cathode, it's difficult to storage the material because the lithium carbonate will adsorb on the surface to affect the capacity. Also, the NCN811 is a very is poor cycle life, and there is a thermal stability issue. So it's very important to improve the cycle life and the safety issue. So you can see for the NCN111 to NCN811, by using the nickel content to 80%, we can increase the capacity and reduce the cobalt to 10% to make a low cost, and also the manganese is to stable the structure. So promote the high nickel content will give a very high capacity and a low price, but it's difficult to make material storage, and the safety issue and the cycle stability will be very poor. So because for the NCN cathode, it's very active on the surface, so there are some side reaction between the cathode and the liquid electrolyte. So the best strategy to avoid the side reaction is make a surface coating. So you can see here for the NCN, a lot of the paper they use different coating technology to avoid the side reaction between the liquid electrolyte and the cathode. So in this study, we try to use the titanium nitride coating on the surface. So first of all, we use the NCN811 coating on the aluminum foil, and we put the electrode into the chamber. So we use the titanium as the target. So we use the vacuum and put the 1-to-1 argon and the nitrogen. So the nitrogen will to attack the target, and finally we can get a titanium nitride coating on the surface. So in order to enhance the homogeneity, we use the rotary, the sample holder, to make a very homogeneous coating. And here we try to use two conditions, is 7 minutes and 10 minutes sputtering time, and to compare the pristine NCN811 7 minutes and 10 minutes. And finally, we assemble the coin cell to test the cycle performance. So here just show how we show the titanium nitride coating. So we just rotate the sample holder and to make the electrode very homogeneous, make a titanium nitride coating on the surface. So first of all, we use the SRD pattern to see the crystal structure change. for the pristine NCA811, titanium nitride 7 and the titanium nitride 10. So you can see it's very similar SRT pattern. It means that there's no impurity on the surface. In order to further identify the critical structural change, we use in the review refinement and to calculate the 007 003 to 104 intensity ratio. The intensity ratio means the cation mixing. So the larger the ratio, it means it's not a cation mixing. So the cation mixing means that the nickel 2 plus is very easy to occupy the lithium plus. So it's a cation mixing. So if the cation mixing occur, it will to create a very poor cyclostability. So you can see for the pristine, the 003 and the 104 ratio is 1.731. But after the titanium nitride coating, the ratio will be increased to 2.2. It means like by using the titanium nitride coating can reduce the cation mixing in the structure. We also use the high resolution TEM to see the titanium nitride coating on the surface. So here is the NCA electrode. So here is the amorphous the titanium nitride. So the thickness is about 1 micrometer. So from here we use a light scan. You can see the titanium nitride is only on the surface, and it's a very homogeneous the coating. Here show the ISPF spectrum after the 5 days in the atmosphere. As I mentioned before, if we use pristine NCA811, we just put the electrode on the atmosphere for 5 days. You can see here it will create some lithium carbonate here. So the lithium carbonate, it will to give very poor capacity contribution. However, after the TiN7 and the TiN10, you can see there is no lithium carbonate on the surface. It means that after the titanium nitride coating on the surface can inhibit the lithium carbonate reaction on the surface. And also we use the titanium nanoscan and the nitrogen nanoscan for TiN7 and the TiN10. You can see the titanium signal and the nitride signal appear in here. So it means that we successfully to make a titanium nitride coating on the surface. So we try to compare the silicon voltammogram at the first cycle for the pristine NCA811 and the TiN7. So you can see from the reduction peak and the oxidation peak, the difference is polarization. So the delta E is 0.58. After the titanium nitride coating for 7 minutes, it will reduce to 0.32 volt. It means that after the titanium nitride coating could be reduced the polarization. Also, we can see at a 0.1 C charge and discharge at the first cycle for the pristine 811, the capacity is only 200 milliamp hour per gram. But after the titanium nitride coating for 7 minutes, the capacity increased to the 220 milliamp hour per gram, and also is the stability is quite good compared to the pristine. We also use the silicon voltammogram for the pristine and after the TiN7 coating at different scan rate, and we can also see the similar behavior. The delta V is 0.66 volt and reduced to 0.51 volt. It means that after the titanium nitride coating for 7 minutes can enhance the kinetics during the charge and discharge process. And also we can use this equation to identify the lithium diffusion during charge and discharge process. So here we use the cycle life at the room temperature and at the high temperature. For the room temperature, we can see the blue color is TRN7, and the green color is the pristine NCN811. So after the base condition in TRN7 have a very good capacity, not only at 0.1 C but also 0.5 C, and also at the high temperature, the TRN7 also give a much better performance compared to the pristine NCN811. Also, we can to monitor the Coulombic efficiency as a function of the cycle number at the room temperature and the high temperature. So you can see obviously at the high temperature, the NCN811 pristine, the Coulombic efficiency is very poor. However, after the TNN coating, not only 7 but also 10, it gives a very high Coulombic efficiency at the 55 degrees Celsius testing condition. So we also to calculate the intensity 003 and 104 again to see the change. So you can see for the pristine 811 and after the 50 cycle, and we can calculate this ratio. The ratio, so you can see for the pristine 811, the 003 104 ratio is from 1.7 reduced to 0.8. However, for the titanium nitride coating for 7 minutes, it will from 2.2 reduced to 0.97. It means that the titanium nitride coating layer could inhibit the cation mixing during the charge and discharge process. So that's the reason why the titanium nitride coating can enhance the cycle stability. We also to test the breakability for the pristine TRN7 and the TRN10. So you can see the TRN7 has a much higher breakability compared to the pristine and the TRN10. We also use the 4-point probe to test the electronic conductivity of the electrode before and after the titanium nitride coating. So you can see here, because the NCA811 is a metal oxide, the conductivity is not so good. So by make a titanium nitride coating, it can be enhance the electronic conductivity. So for 7 and 10, the conductivity could be increased a lot compared to the aluminum foil. So we also use EAS spectrum to see the impedance. So you can see the left-hand side is the fresh. The right-hand side is the after the charge and discharge for 3 cycle. It's a formation step. So from here we can see for the pristine, the RSEI impedance is very high. And also the RCT charge change resistance is also very high. However, after the titanium nitride coating on the surface, the dramatically reduced is the RSEI. It means like by using the titanium nitride coating on the surface will be create the artificial SEI on the surface to inhibit the CEI formation during the charge and discharge process. So here shows the electrode after 50 cycle. So you can see this one is the pristine 811. After 50 cycle, you can see some cracks on the surface. However, after the TNN coating for 7 minutes, so it's still very stable structure. So the titanium nitride coated 811 demonstrate a much stable structure even after the 50 cycle. And also we use we charge discharge our electrode and open the coil cell to test the SPS, to try to evaluate the CEI formation and the CEI composition. So from this data, we can see that because we use a titanium nitride coating on the surface of the NCN-A11, so it will create the lithium nitride and the lithium fluoride rich, the artificial SEI, to protect the NCN cathode from the HF attacking. Also, the titanium nitride protect the NCN-A11 electrode could be inhibit the formation of the lithium carbonate. We also use the DSC to see the thermal stability. So we charge our electrode and we open the cell and put the electrode into the DSC sample holder, and we'll put one drop the liquid electrolyte to monitor the battery performance, and we heat the sample holder. So as you can see here, for the pristine A11 is the red color. The only 240 degrees Celsius is a dramatically peak shown here. But after the titanium nitride coating, you can see the peak area reduced a lot. Also, the reaction will extend it to the 218 degrees Celsius. So it means that the thermal stability could be improved and enhanced after the titanium nitride coating. Finally, we use the in situ SRT measurement to see the NCN-A11 and the TIN7 to see the evolution of crystal structure during charge and discharge process. So we can calculate the lattice constant and compare here. So from our comparison, after the titanium nitride coating, the lattice change stability could be enhanced a lot after the titanium nitride coating. And also, we try to assemble the punch cell by using the NCN-A11 and the titanium nitride 7 as the cathode, and using the graphite as the anode to assemble the punch cell. So you can see here, the cycle stability is very good, and also the rate capability is also very good. So it means that by using the titanium nitride modified, the NCN-A11 could be used for the punch full cell in the future. So the mechanism is by using the plasma assisted titanium nitride modified NCN-A11, show very good thermal stability and also good structural stability. So here is the mechanism. Without the NCN-A11, without titanium nitride coating, it shows a very poor SEI formation. Also, because the surface of the NCN-A11 is very active to react it with the liquid electrolyte. Also, it's a very poor CEI formation. But after the titanium nitride coating, not only enhance the electronic conductivity of the NCN-A11, but also the artificial SEI could be benefit the lithium charge and discharge process and inhibit the cell reaction between the electrolyte and the cathode materials. So the paper is also published in the Chemical Engineering Journal in 2023. We also filed a patent in Taiwan and the US. So finally, I'll give a conclusion. In this talk, I propose the atmosphere pressure plasma treatment to improve the electrode performance of the soft carbon by surface modification and the nitrogen doping technology. So by using the 14 times the argon plasma treatment, give a very good electrochemical performance. And also the surface will become hydrophilic, and nitrogen doping can improve the rate capability and the cycle life. The second part, we use the titanium nitride coating on the surface of NCN-A11, not only enhance the cycle stability, but also the thermal stability. Of course, the titanium nitride could be inhibit the lithium carbonate formation, and also benefit to the good CEI formation on the surface. So finally, I will thank financial support from NTC and my student, and thank you for your attention.
Okay, thank you very much, Professor Liu. And well, do we have question from the audience? You can, of course, you can write in a chat box, okay? Because you cannot access to microphone. Yes, we have one question from Gopal.
Okay. So the plasma treatment, is there any phase change? Yeah, because plasma treatment is only on the surface instead of the whole structure. So from the SRD measurement, not only in the soft carbon but also the NCA-A11, we can see the phase purity is maintained. So it's only the we can. So I don't think so. Is there any phase change, and also the crystallinity after the plasma treatment because it's only on the surface. And we also use the TIN coating. Yeah, because for the TIN coating, there are so many published papers. They try to use the lithium nitride rich, the SEI, because the lithium nitride is a very good component for the SEI or CEI formation. So for the TIN coating, the lithium will react it with the nitride to make a lithium nitride composition. So the artificial SEI could be better for the cycle performance. And also physically, the titanium nitride coating can enhance the NCA-A11 electronic conductivity. So it's both from the chemical viewpoint and the chemical viewpoint.
Okay, do we have more questions from the audience? Well, I wonder about the stability of the NCM. And once we have a layer of titanium nitride on the, of course, on the at the surface, does it change the stability window of NCM?
You miss the titanium nitride coating on the surface of the cathode, right?
Yes.
So sorry, what's your question?
Oh, okay. Sorry.
Stability?
Stability. Yeah.
Okay. Because for the cycle stability, both in the room temperature and the high temperature, the cycle stability is also very good. Because the artificial SEI could be benefit the cycle performance during charge and discharge process, especially in the high temperature. So as you can see at the 55 degrees Celsius, the Coulomb peak efficiency dropped a lot for the pristine cathode, but for the TIN protect the TIN coating, the NCA-A11, the Coulomb peak efficiency will enhance a lot for the Coulomb peak, for the high temperature.
Okay, so it's more stable. I mean, well, in it can tolerate not only temperature but also the voltage also, right?
Yeah, because the manganese will dissolution during charge and discharge process, but after the titanium nitride coating could also be inhibit the manganese to dissolve in the liquid electrolyte.
Okay, and also, well, I mean, well, the decomposition of the NCM, which is resulted from
Yes, yes,
high
yes,
voltage, yeah, also prohibited.
yes,
Yeah. Okay.
yes.
Okay, so do we have more questions? from the floor, from the audience. And well, titanium nitride, I feel like, of course, so many people apply it
Mm.
on different components, of course, on even
Okay.
the anode of the the zinc ion battery, of course. Somebody, wow, so
Oh,
many people use titanium nitride surface, yeah, to mitigate the
okay.
dendrite formation of zinc, something
Yes.
like that. Yes.
Mm.
Mhm.
Mm.
Okay, so wow. Do we have more questions from the audience? No? If not, wow, thank you very much for wow your excellent talk, and thank you for your time. Yeah,
You're
I'm
welcome.
really happy that to
Yeah.
have you here. Yeah, in
Yes.
our webinar. Yes.
Yes.
Okay. Yes, thank you very
Okay.
much. And of course, the audience, if you have more questions later, you can contact Professor Liu directly.
Okay.
Okay, thank you. Thank you very much.
Thank you. Thank you.
So yeah, I need admin to finish to close the webinar also.